The 5,750-ton protected cruiser HMS Gladiator, an armored deck cruiser rather than a heavily side-armored battleship, was dying from an unsolvable physics problem. A catastrophic breach along her starboard side had initiated uncontrollable asymmetrical flooding, with thousands of tons of seawater rushing into open compartments and shifting her center of gravity. The crippled cruiser was in the final stages of capsizing. In April 1908, the Royal Navy cruiser was navigating the western Solent off the northwest coast of the Isle of Wight near Fort Victoria. The operational conditions were severe. A freak springtime snowstorm had descended over the channel, and visibility at the time was reported at around 800 yards. The blinding weather masked the movements of other vessels in the congested shipping lane. Steaming through the whiteout, the crew of the Gladiator found themselves suddenly sharing the restricted waterway with a massive outbound American passenger liner, the SS St. Paul. The two vessels were locked on an intersecting course. Due to the heavy snowfall and the strong tidal currents of the channel, there was neither the visibility nor the reaction time necessary to execute a successful evasive maneuver. The SS St. Paul, essentially a reinforced steel wedge that had slowed to roughly 3 knots in the whiteout, slammed violently into the starboard side of the Gladiator. The impact struck at an angle, but it still hit just aft of the main engine room. A huge share of the liner's momentum drove into the warship's hull, to buckling plating and frames on impact. The bow of the St. Paul tore open a devastating gash. Accounts variously describe it as roughly 40 to 50 feet long and around 20 feet high. The intrusion reached deep into the ship, in places on the order of a dozen feet, ripping into internal decks and machinery spaces. When the American liner inevitably reversed her engines and pulled away from the entanglement, the action unsealed the wound. The shattered compartments were instantly exposed to the open ocean. Seawater surged through the torn plating with brutal force. Because the damage was concentrated on the starboard side, flooding spread unevenly across the ship. Compartments on the starboard side began filling rapidly, piling weight off-center and driving the cruiser into a steepening list. Below decks, engineers fought to shut watertight doors and contain the spread, but the inflow overwhelmed what could be sealed and what could be pumped. With deep water sinking now minutes away, the captain made a desperate operational decision. He abandoned any attempt to save the vessel as a freely floating asset and instead chose to weaponize his remaining momentum. He ordered the helm to steer the dying cruiser directly toward the shore of the Isle of Wight, aiming for a shallow sandbank situated near Fort Victoria. The captain deliberately traded his maneuverability for a hard grounding. The singular goal was to drive the ship aground before the rapidly increasing list caused her to roll entirely upside down and sink in the deep shipping lane. The Gladiator plowed into the coastal shelf, her keel violently digging into the sand. However, for the physical beaching maneuver could only halt her forward motion. It could not stop the off-center water already trapped inside her hull. The list kept growing. Within minutes of the collision, the 5,750-ton warship rolled over and capsized onto her starboard side. She lay crippled just off the shoreline, her port side still exposed above the water while the crushed starboard side pressed into the bottom. Grounding had prevented a deep water sinking, but it left the hull perched on a narrow sandbank ledge near Sconce Point, with a steep drop into the shipping channel immediately beside her. If the bank failed under tide and scour, the flooded cruiser could slide into deep water and be lost beyond any realistic recovery. This precarious resting position created a constant gravitational shear, or the flooded hull's weight was no longer directed straight down. The angled bank pushed part of that force laterally toward the channel. Tidal currents washed over the wreck and scoured away loose sediment, while mud under the ironwork reduced friction and encouraged creeping movement. Each hour increased the risk that the ship would slip off the ledge into deep water, an outcome that would submerge her completely and likely end any chance of recovery. Normally, engineers would anchor salvage craft nearby, run heavy wires to the wreck, and use powerful winches to start the roll. But Gladiator lay on the edge of a bank, and any strong sideways pull from a float risked dragging the hull toward deep water before it could rotate. Until that geometry was controlled, a conventional floating pull was too dangerous to attempt. That instead of treating the operation as a purely offshore job, the recovery commander shifted the main hauling power onto solid ground. Captain Frederick H. Young of the Liverpool Salvage Association recognized that, with the wreck perched near deeper water, the safest leverage would come from the shore. Near Fort Victoria, crews installed steam-driven hauling engines and heavy bollards set in concrete, so the pull came from an anchor that could not drift or drag. With the unyielding terrestrial foundations permanently locked into the earth, the salvage crew began the arduous physical task of connecting the land directly to the sea. They deployed incredibly heavy steel wire hawsers. Moving steel cables of this diameter across open water is a brutal physical endeavor, requiring specialized boats and block systems just to support the dead weight of the iron ropes. These massive steel lines were carefully routed from the steam winches on the beach out toward the wreck. The rigging crew then attached the 2-inch cables to the uppermost sections of the exposed portside hull. To ensure the attachment points did not simply tear out under extreme load, the thick steel ropes had to be securely fastened to the strongest internal framing ribs of the warship. Connecting the wires to the high port side created tremendous leverage, maximizing the turning moment that the shore winches could exert on the capsized hull. Applying tension to this sprawling system required deliberate mechanical synchronization. The steam winches slowly ground forward, taking up the slack in the heavy cables. As the lines lifted out of the water, they pulled taut, transforming from drooping ropes into rigid steel rods of immense potential energy. This mechanical tether created a permanent locked geometry between the concrete foundations at Fort Victoria and the iron hull of the cruiser. With the hull now restrained from slipping seaward, the engineers finally had a stable line of pull for the righting attempt. But the wreck was still embedded in mud, and turning force alone could not break the seabed's suction. They needed lift as well as tension. To break the seabed's grip without ripping the cruiser apart, the team faced a brutal trade-off. Enough force to turn a flooded steel structure, but not so much that the hull failed. A single hard pull from the beach would risk tearing upper structure away. The wreck had to be lifted as it was turned. The solution was to add external lift with large lifting pontoons, sometimes described as camels, so the wreck could be coaxed up without a single brutal pull from a float. Divers and riggers worked them into position and fastened them to the hull. Then, by using compressed air to drive water out of those pontoons, the salvers could steadily build buoyant lift beneath the ship, helping break the grip of mud and reducing the risk of tearing the hull during the roll. This synchronized application of force created a perfect combined righting moment. The heavy terrestrial wire ropes constantly hauled the exposed port side toward the shore, forcing the top of the vessel to rotate inward. Simultaneously, the buoyant lifting power of the submerged camels pushed the buried starboard hull violently upward toward the surface. Working in unison, the lateral tension from the land and the vertical thrust from the ocean generated a massive rotational torque around the central axis of the wrecked hull. The mechanical objective was to forcefully pivot the mass over its own lower bilge, turning a capsized wreck into a stable vertical structure. However, Gladiator's structure was built to share loads while afloat, not to take brutal, uneven stresses while pinned to a shelf. Mud and sand had sealed around the starboard side like a vacuum, and breaking that suction demanded immense force. Applied too fast, that force could fracture the keel and snap the ship in half. Consequently, the salvage commanders refused to rush the mechanical execution, and the righting was phased over months. Shore-based hauling tightened inch by inch, while added buoyant lift was increased in careful steps. Over that grind, the suction of coastal mud was gradually broken and the hull was eased back toward an even keel, with the effort reaching its decisive stage in early October 1908. The prolonged mechanical siege was a profound operational success, effectively righting the heavily armored vessel exactly where she lay on the submerged shelf. The combined lifting moment conquered the challenging geometry of the wreck, successfully pivoting the tremendous mass into a standard upright configuration. Yet, while the massive dead weight had been mathematically returned to an upright orientation, the structure remained fundamentally non-buoyant. The extensive internal compartments were entirely unsealed and thoroughly flooded with the sea, leaving the salvaged hull upright but entirely unable to float. To transform a flooded iron monolith back into a buoyant vessel, the engineering team had to weaponize the internal volume of the hull itself. An upright ship sitting fully flooded on the seabed possesses absolutely no natural buoyancy. It is merely a heavily armored container holding thousands of tons of heavy ocean water. To break the final grip of the seafloor and lift the vessel toward the surface, the salvers had to artificially recreate the hydrostatic displacement that originally allowed the massive structure to float. This required the deliberate manipulation of internal pressure. However, initiating this phase demanded the creation of a rigid, watertight boundary. The cruiser was still suffering from massive structural trauma. The original hull penetration remained completely open to the sea. If the heavy machinery was activated while the hull remained breached, the engines would simply be attempting to pump out the entire ocean. The water level inside the ship would never permanently drop. Therefore, the marine engineers had to execute extensive underwater construction to isolate the damaged compartments from the surrounding environment. Specialized divers descended into the dark water to address the massive exterior breach. They built heavy temporary shoring and patching in timber, tightening it against the torn plating to reduce the free exchange of water. At the same time, teams inside the newly righted ship reinforced what bulkheads they could reach, braced doors, and wedged leaks wherever the structure had warped. The singular goal was to establish a workable seal around the core volume of the ship. Once the physical boundary was rigidly secured, the recovery commanders deployed a massive array of heavy centrifugal salvage pumps. These powerful steam-driven units were positioned precisely above the deepest flooded compartments. Massive intake hoses were lowered directly into the flooded engineering spaces. When the coordinated operation commenced, the synchronized mechanical pumps began violently pulling heavy seawater out of the lower decks and discharging it directly overboard into the channel. The physical mechanics of internal pumping represent a direct transfer of mass. As the heavy seawater is mechanically evacuated from the internal chambers, it is replaced entirely by empty air. This newly created internal void violently alters the mathematical equilibrium of the hull. The surrounding ocean pushes relentlessly against the exterior of the newly sealed ship. Because the heavy water inside is no longer present to push back, the external hydrostatic pressure exerts a tremendous upward force against the empty lower compartments. The ocean itself supplies the vital lifting energy, striving aggressively to push the hollow structure upward toward the surface. Through the month of October, the relentless discharge of internal water steadily increased this upward hydrostatic pressure. The internal water level dropped lower and lower, steadily increasing the artificial displacement of the hull. The structural tension mounted significantly as the rising buoyancy fought fiercely against the remaining dead weight and the sticky mud of the coastal shelf. Eventually, the mathematical balance completely inverted. The total volume of evacuated water generated enough pure hydrostatic lift to completely overpower the remaining total mass of the warship. The immense iron hull finally broke free from the seafloor. The enormous vessel rose quietly through the water column and settled firmly onto the surface. She was no longer a sunken marine hazard, but an actively floating asset. The rigorous recovery phase concluded as an absolute mechanical victory. Standard tow lines were securely attached to the bow, and a coordinated fleet of towboats carefully pulled the battered cruiser away from the dangerous coastal shelf. She was successfully navigated through the local channels and towed directly into the safety of the naval facilities at Portsmouth. The massive deadweight was successfully a functioning vessel once again, completely rescued from the hostile ocean environment, yet her ultimate structural and financial viability inside a dry dock remained entirely untested. The recovery of the wrecked cruiser was an absolute engineering triumph that mathematically collided with a brutal economic reality, with the salvage bill reported at around £50,500 and the eventual sale bringing in about £15,125. The immediate operational mandate had been perfectly executed. The massive deadweight of the warship was successfully rescued from the coastal shelf, refloated, and navigated back into the heavily fortified naval dockyards at Portsmouth. The salvage commanders had defeated the hostile ocean, but successfully returning a floating steel hull to a dry dock did not mean the vessel was functionally alive. Once the heavy steel gates of the dry dock were securely closed and the massive industrial pumps drained the surrounding water, the true extent of the structural devastation was completely exposed. The visual reality was catastrophic. The impact gash from the American liner was only the most obvious trauma. The secondary damage inflicted by the environment and the salvage process itself was profound. 5 grueling months submerged in the corrosive saltwater of the channel had utterly destroyed the complex internal systems of the ship. The advanced steam engines, the intricate mechanical linkages, the early electrical wiring, and the heavy artillery mounts were all heavily compromised. Deep coastal mud had penetrated every open hatch and filled every mechanical tolerance with highly abrasive sand. Furthermore, the extreme mechanical forces required to rescue the hull had fundamentally altered its structural integrity. The relentless longitudinal tension and the massive upward thrust required to break the suction of the seafloor had applied severe stress to the entire iron framework of the ship. While the heavy skeleton had survived the incredible turning moment without snapping, the massive hull was warped, heavily strained, and thoroughly exhausted. The British Admiralty was immediately forced to confront a severe financial and tactical calculation. The concept of economic attrition dictated the fate of the battered vessel. The specialized heavy marine recovery operation had already drained £64,000 from the military budget. This enormous expenditure covered the rapid deployment of heavy infrastructure, the continuous operation of winding machinery, the specialized diving crews, and 5 relentless months of intensive industrial labor. That tremendous cost had merely stabilized the wreck and brought it home. Actually, repairing the warship to a combat-ready state would require a massive secondary investment. The shipyards would essentially have to gut the entire interior, rebuild the shattered starboard armor plating, realign the stressed keel, and install entirely new propulsion systems. The mathematical equation was completely unviable. By the time the vessel rested in the dry dock in 1908, the rapid advancement of global naval technology had already rendered her fundamental design highly obsolete. She was an older generation of protected cruiser, outclassed by newer, faster, and heavily armed vessels currently rolling off the slips. Committing vast sums of national capital to resurrect an outdated and severely compromised hull was a strategic impossibility. The warship possessed absolutely zero remaining tactical value to the fleet. Consequently, the Naval Board officially declared the vessel to be fundamentally beyond economic repair. The physical survival of the hull was ultimately irrelevant to its military utility. The Admiralty dispatched crews to systematically strip the ship of any surviving armaments, salvageable brass fittings, and reusable internal components. Stripped of her military identity, the immense iron shell was reclassified as raw industrial material. The Naval Command sold the remains of the cruiser in 1909 to a Dutch shipbreaking firm. The final chapter of the operation proved the absolute cruelty of maritime economics. The heavy marine engineers had executed a flawless sequence of mechanical logic to defeat the hostile environment of the channel. Yet, despite their absolute technical victory over the coastal geography, the shipyard mathematics completely erased their reclaimed prize. The operational mandate had always been to recover the physical vessel from the grip of the sandbank, but it could not guarantee a future for the asset itself. The cruiser was dragged back from the abyss strictly to be systematically cut apart for scrap iron, leaving the salvage record as a permanent testament to an engineering triumph that ended in total financial exhaustion.